One of the hallmarks of a linear transformation, and by that I mean the thing that sets it apart from just any old function that may or may not be linear in the sense of satisfying the conditions of a linear transformation. The thing that sets linear transformations apart is that their action, so to speak, in the sense of the things that they accomplish or get done, can be always achieved through matrix multiplication. That's actually something that all linear transformations have in common, and it's going to turn out only linear transformations have that property. But we'll talk more about that in the next section. But for now, I just want to show you what I mean. So if we were to scroll up to the example we did 2 pages ago, this example right here, I'll number this as example 1 because I'm going to refer to that right now. And actually, I'll leave this in yellow, and I'll just write the number 1 here so you can see what I mean. So this function was defined by t of x1, x2, because the domain was R2, and the codomain was also R2, and the output value was this, x1 minus x2 for the first coordinate, and then 3x2 for the second coordinate. Now the second example that we looked at, that's this one here on the previous page. You can see the definition here, but I'll just write it down. It's given by t of x1, x2. Again, the domain was R2, but the codomain was R3 this time. And the definition was the output vector was of this form, x1, x2, and then the third coordinate was the sum of x1 and x2. Okay, I want to show you what I mean by the fact that these can be realized through matrix multiplication. By the action, I mean the thing that turns this vector into this vector. Okay, let's start with the first one. And don't worry too much about why I'm doing these steps. Okay, I just want you to believe the steps and be convinced at the end. I'm going to split this up as the sum of two vectors. I'm just applying properties, I'm just applying properties of vector arithmetic. So it's going to be x1, 0 plus negative x2, 3x2. This is kind of like when we write the general solution of a linear system in parametric vector form. I'm kind of following that same approach, except instead of parameters, I've got, well, these actually are, technically these are parameters, just the word is being used in a different context here, but I'm treating the variable unknowns here as parameters. So now, I split this up into the sum of two vectors, one of which has all the x1 stuff and the other one that has all the x2 terms. And then I'm going to actually factor out the x1. So I've got x1 times the vector 1, 0 plus x2 times the vector negative 1, 3. Okay, now why did I do that? Well, this is actually the definition of this matrix product. If I were to take this 2 by 2 matrix, notice I'm just taking those two vectors and putting them together as columns and multiplying that 2 by 2 matrix by the 2 by 1 vector with unknown coordinates x1 and x2. See how we did that? If you were to actually go look back to section, what was it, 1.4 or 1.5, when we talked about matrix multiplication, the definition of multiplying a matrix by a vector is you take these entry coordinates of the vector and you multiply them by these columns, and then you add up the scalar products, which is exactly what we've done here. So the point is, by left multiplying the vector x1, x2 by this 2 by 2 matrix, you have the same effect as applying t. So let me add an annotation here. So this matrix, contains the essence of t. Okay, and there's a more efficient way to find this matrix, but for now I just want to convince you that this works, and I don't want to develop that much machinery to do it. But you can follow the same approach with this example. I can write this as x1, 0, x1 plus 0, x2, x2. And then I can pull out my parameters, and I get x1 times 1, 0, 1 plus x2, 0, 1, 1, and I can write that as the matrix product of this 3 by 2 matrix by this two-dimensional vector here, x1, x2. This matrix product is literally defined to give you this. So again, you can look at this as the definition of t, but to go from here to here, that's what t really does. You can do that by just taking that vector that we started with. That's the input vector over here, right? Left multiply it by this 3 by 2 matrix, and that's going to give you the same thing. So that's what we mean when we say that linear transformations can be realized through matrix multiplication. So if you were to change a function, if you were to change the definition of the function, as long as it's a linear transformation, there would be some matrix you could determine that would do the job through left multiplication, do the same job that that function does. That's the neat thing about linear transformations. And if you were to just, what if you skipped the first part, like don't even have a rule? What if you don't even define the function in terms of a formula like we did in the previous two examples? What if you just were given the matrix right off the bat? And that's what this next fact is mentioning. So let's say we had an m by n matrix. I'm not going to make any assumptions about it. Just it's some matrix. Well, right away, that's enough to define a linear transformation. And here's how you do it. It's a linear transformation that's going to go from Rn to Rm. And this time, I'm going to zoom in because this is important. The number, well, it's all important, but the notation is hard to see, and this is important. So the number of coordinates of your input vector is going to have to be exactly the same as the number of columns of your matrix A. And the number of coordinates of your output vector is going to have to be the same as the number of rows of your matrix A. And all this has to do with, this just comes from the way matrix multiplication works, when you multiply a vector by a matrix. And this is actually, I said a while ago, there's an important reason why we really want to represent vectors as column matrices whenever we can. And there's some times when you're going to want to violate that and go into different, use different notations, but it's very convenient to represent vectors in column notation specifically so that matrix multiplication will work out. Okay, but this is the definition. This now defines the rule. If you want to plug in an input vector x that has n coordinates, and if you want to determine the output vector, I kind of circled the wrong thing. If you want to determine the output vector, just multiply it on the left by a, and that will turn your n-dimensional vector x into an m-dimensional vector a times x. So that's you're going to plug in a vector x, and you're going to get out a vector a times x, which is going to turn out to be m-dimensional. And the reason it's going to be m-dimensional is because the number of rows of the matrix A is m. Okay, how do you know this is a linear transformation? Let's prove this. And before you groan, you might think, oh man, this is going to be a lot of work. Because this is in the previous two examples we took, this is a non-trivial amount of work to show that this is a linear transformation, and here to show that this is a linear transformation was a lot of work. So now we're in a situation where we don't even know the definition of the matrix or of the linear transformation. We're just told that it's defined through left multiplication of this matrix, and I'm not even telling you what the entries of this matrix are, and I'm not telling you what m or n is. You might be tempted to think that this is going to be even more work, but actually, it's funny. Sometimes the less detail you have, the simpler the proof gets, and I'll show you what I mean by that. How do you show something's a linear transformation? Because that's what we're asked to do. We're asked to prove this fact. Well, how do you do it? Well, show that it satisfies the two conditions, right? So let's start by, let's say, let u and v be an Rn. Turns out I don't even need to write down coordinates this time. Okay, let's write down t of u plus v. Okay, well, what's t of u plus v? Well, it's a times u plus v. That's the way this transformation t was defined. If you want to figure out what an output vector is, just multiply your input vector by the matrix A. So that brings us here. But remember, now we're talking about matrix multiplication. There's a nice property called the distributive property here. We can just distribute the A into the brackets, and that's why this works out so nicely. We can just say this is A times U plus A times V, and guess what? That's exactly T of U plus T of V. Okay, perfect. That was a one-liner, and they weren't very thick lines. There wasn't writing all over the page, right? That's the first condition. Okay, what about the second condition? Well, we need a vector, let u be in Rn, and we also need a scalar for the second condition. And then we need to show that t times the scalar times the vector, or sorry, t of the scalar times the vector, is going to give us c times the c times t of the vector. So we want to get c times t of u back as the end. But let's just start by using the definition. How do you apply t? You multiply the input vector by a. So we're going to have a times cu. Okay, well there was another property, and it's right immediately after we proved this property in the notes. We had another property stated, which says that you can pull the scalar out. I hope you thought about this and worked out the details, but this was the very next property. If you have a scalar times a vector, which is what you have inside the brackets, and then you want to multiply that by a matrix, that's the same as if you just multiplied the matrix and the vector beforehand and then multiplied the scalar on after. That was one of our other properties that we have available for matrix multiplication. So this turns out to be really convenient here, because now that's exactly c times t of u. Okay, so that's the end of it. That's exactly what you need to do to prove something's a linear transformation. So we can say, therefore, t is a linear transformation. Okay, so the idea is, if you have a matrix A, you can use it to define a linear transformation in this fashion. And if you have a linear transformation, like one of the ones up here, you can use this technique that we just showed to identify it with a specific matrix. This one-to-one correspondence works both ways, and it turns out every transformation has its own matrix, and it's called the standard matrix of the transformation, which we're going to talk about more in the next section, but that's a little bit of a preview for you.